In the world of electronics, you've got your rock stars, and then you've got the quiet heroes working behind the scenes. Today, we're pulling back the curtain on one of those unsung components. It's literally everywhere, and without it, well, our modern world just wouldn't work. So let's get right into it. So, when you think about the absolute basics of electronics, right? The fundamental building blocks, I bet two components jump to mind immediately: the resistor and the capacitor. But here's the thing. It's not a duo, it's actually a trio. There's a third player on the team, and it's just as important. First up, you've got the resistor. Super straightforward. Its job is basically to act like the brakes in a circuit. It just opposes the flow of current, and it turns that electrical energy into heat. Simple, right? But totally essential. All right, then we have the capacitor. You can kind of think of this one as a tiny, super fast battery. It holds on to energy in an electric field, just waiting to let it all go in one quick burst. Okay, so we have one component that resists and another that stores energy in an electric field. So that leaves our mystery guest, the third one. What on earth is its job? What special trick does it have that the other two don't? And that third component is the inductor. Now, its secret sauce, its whole reason for being, isn't to oppose current. No, it's to oppose any change in the current. And how does it do that? By storing energy in a totally different way, inside a magnetic field.
When you get right down to it, an inductor is beautifully simple. I mean, it's really just a coil of wire. That's it. Sometimes it's wrapped around something called a core, but the idea is simple. You push current through that coil, it creates a magnetic field, and boom, that's where the energy is stored.
And this right here is the absolute key to understanding inductors. See, it doesn't care one bit about a steady, constant current. It'll just let that flow through all day long. But the second you try to change that current, that's when the inductor wakes up and fights back. Try to ramp up the current, and its magnetic field expands to push against you. Try to cut the current, and that field collapses, trying desperately to keep it going. So you can almost think of it as a little four-act play. First, you flip the switch. As the current tries to surge, the inductor creates this reverse voltage. We call it back EMF, and it fights that increase. Then, once the current levels out and everything's steady, the inductor basically goes to sleep. But then, you cut the power. And as that magnetic field collapses, it generates a forward voltage, giving one last push to keep that current flowing, just for a split second. Honestly, the best way to think about an inductor is like a big, heavy flywheel, It takes a lot of effort to get it spinning from a dead stop. But once it's going at a steady speed, it's easy. And if you try to just suddenly stop it, whoa, it's going to fight you with all that momentum. That's exactly what an inductor does for electricity. It's electrical inertia. Okay, so we've got the concept down, but how do we actually, measure this stuff? How do we predict what it's going to do? Well, that's where we get into a really cool law of physics and the special unit that goes with it. Yeah, this whole fighting against change thing isn't just some quirky personality trait of an inductor. It's actually a fundamental law of the universe called Lenz's law. Basically, it says that nature just hates a change in magnetic flux. So the voltage an inductor creates, that EMF, will always, and I mean always, push back against the very thing that's causing the change. And the best part is we can boil that entire law down into this one super elegant formula. It just says the voltage, V, across the inductor is its inductance value, L, times how fast the current is changing. That's the dI over dt part. So it's simple. A bigger inductor or a faster change in current means a bigger pushback voltage. That's it. So that L we just talked about, we measure that in a unit called the Henry, named for the American scientist Joseph Henry. But here's a fun fact. 1 Henry is a huge amount of inductance. I mean, massive. In the real world, in the electronics you actually use, you're going to see much smaller values like millihenries, microhenries, or even tiny nanohenries. Okay, let's make this real. Let's say you've got a pretty beefy 5 Henry inductor, and you change the current flowing through it at a rate of 4 amps every second. You just plug those numbers into the formula, and you get 20 volts. That's a serious amount of opposing force that the inductor is creating all on its own. But of course, not all inductors are created equal. It's kind of like tools in a toolbox, right? You need the right one for the job. And for inductors, what really matters is the material inside the coil. That's called the core, and it completely changes how the inductor behaves. Let's look at the two extremes. On one end, you have an air core inductor. It's exactly what it sounds like, a coil of wire with just air in the middle. The inductance is pretty low, but that makes it perfect for super high frequency stuff, like the radio signals in your Wi-Fi router. Then on the complete opposite end, you've got an iron core. You shove a chunk of iron in there and it boosts the inductance like crazy. This is what you want for big, low-frequency power jobs, like in a transformer. The downside? They're big and heavy. But in most modern gadgets, the real king of the hill is the ferrite core. It's this cool ceramic material that gives you the best of both worlds. It's got good inductance, and it's great at high frequencies. That's why you'll find them inside pretty much every phone charger. And then there's the specialist, the toroid. It's shaped like a donut, and its superpower is keeping its magnetic field all tucked in so it doesn't interfere with anything else. Super clean. So let's do a super quick recap. Air core, think radio and Wi-Fi. Iron core, think big power, like transformers. Ferrite, that's the all-arounder, the workhorse inside your phone charger. And toroidal, that's for when you need things super clean and quiet, like in fancy audio gear. Every single one has its own special job. All right, so we've covered what an inductor is and how it works. But now we get to the really cool part. Where are they? Because I promise you, you are surrounded by these things right now, and you probably have no idea. Okay, look outside. See those big gray cylinders on the power poles? Those are transformers. And a transformer is really just two inductors sharing a core. They use their magnetic fields to change the voltage, stepping it way down so the power that comes into your house is safe to use. Got solar panels on your roof? Well, you've got inductors too. Inside that inverter box on the wall, there's a special boost inductor, and its whole job is to take the low voltage coming from the panels and jack it up to match the voltage of the power grid. And yep, that little power brick you plug your phone into every single night, go ahead and pick it up. There's a tiny but super important ferrite inductor inside there, switching on and off thousands of times a second, storing and releasing energy to charge your phone without wasting a ton of power. And it doesn't stop there. Inductors are literally the heart of every electric motor, using those magnetic fields to create motion. They're also used as filters, sometimes called chokes, to block out all the electrical noise on your power lines, making sure all your sensitive electronics get clean, stable power. So you see, from the giant power grid all the way down to the tiny charger in your hand, this simple coil of wire is the unsung hero. It's smoothing, converting, and filtering the energy that powers our entire world. And it really makes you think. As we push for technology that's even faster and more efficient, what's next for this humble component? How will this simple coil of wire continue to shape our future?